Today we're going to talk about hypothesis tests for two-sample means. We need to talk about the assumptions and conditions first. The independence assumption. Each condition needs to be checked for both groups. The randomization condition. Were the data collected from suitable randomization? The 10% condition. We don't usually check this condition for differences of means. We will check it for means only if we have a very small population or an extremely large sample. The normal population assumption. This must be checked for both groups. A violation by either one violates the condition. The independent groups assumption. The two groups we are comparing must be independent of each other. If not, we will discuss this later in the lesson. The hypothesis test we use is the two-sample t-test for means. The conditions for the two-sample t-test for the difference between the means of two independent groups are the same as for the two-sample t-interval. We test the hypothesis mu sub 1 minus mu sub 2 equals delta sub 0, where the hypothesized difference delta sub 0 is almost always 0. Using this statistic, t equals x bar 1 minus x bar 2 minus delta sub 0 divided by the square root of s1 squared over n1 plus s2 squared over n2. When the conditions are met and the null hypothesis is true, this statistic can be closely modeled by a student's t-model with a number of degrees of freedom given by a special formula. We use that model to obtain a p-value. Let's take an example. The Better Cookie Company claims its chocolate chip cookies have more chips than another chocolate chip cookie. 120 Better cookies and 100 of the other type of cookies were randomly selected, and the number of chips in each cookie was recorded. The results are as follows. For the Better Cookie Company, we had a mean number of chips of 7.6 and a standard deviation of 1.4. For another cookie company, we had a mean number of chips of 6.9 and a standard deviation of 1.7. At the 2% level of significance, test the claim that the population of Better cookies has a higher mean number of chips. Step 1, our hypothesis. So, our parameters are mu sub 1 is the population mean number of chips from Better Cookie Company, and mu sub 2 is the population mean number of chips from another cookie company. Our null is mu 1 equals mu 2, and our alternative is mu 1 is greater than mu 2. Checking our assumptions and conditions. We have a simple random sample, it's stated. Sigma is unknown, so we'll use a t-distribution. Populations are independent, and since we don't have the data, we can't determine if we have a normal distribution, so we'll assume that we have an approximately normal distribution. Step 3 is to calculate the test. Our t is equal to 7.6 minus 6.9 minus 0 over the square root of 1.4 squared over 120 plus 1.7 squared over 100. We get t equals 3.29. Drawing our normal curve and shading to the right of 3.29, we get a p-value of 0.0006. So, the probability that the difference between the sample means is 0.7, given that there is no difference in the population means, is 0.0006. Our conclusion: since p-value is less than alpha, our alpha is 0.02, we reject that there is no difference in population mean number of chips between Better Cookie and another cookie company. Paired data. Data are paired when the observations are collected in pairs or the observations in one group are naturally related to observations in the other group. Paired data arise in a number of ways. Perhaps the most common is to compare subjects with themselves before and after a treatment. When pairs arise from an experiment, the pairing is a type of blocking. When they arise from an observational study, it is a form of matching. If you know the data are paired, you can and must take advantage of it. To decide if the data are paired, consider how they were collected and what they mean. There is no test to determine whether the data are paired. Once we know the data are paired, we can examine the pairwise differences. Because it is the differences we care about, we treat them as if they were the data and ignore the original two sets of data. Now that we have only one set of data to consider, we can return to the simple one-sample t-test. Mechanically, a paired t-test is just a one-sample t-test for the mean of the pairwise differences. The sample size is the number of pairs. Our assumptions: the data must be paired, the differences must be independent of each other, we need to assume that the population of differences follows a normal model. We can check this with a histogram or a normal probability plot of the differences. When the conditions are met, we are ready to test whether the paired differences differ significantly from zero. We test the hypothesis that mu sub d equals delta sub 0, where the d's are the pairwise differences and delta sub 0 is almost always 0. We use the statistic t equals x bar sub d minus delta sub 0 over s sub d divided by the square root of n, where n is the number of pairs. When the conditions are met and the null hypothesis is true, this statistic follows a student's t-model on n-1 degrees of freedom, so we can use that model to obtain a p-value. Let's look at an example. A test of abstract reasoning is given to a random sample of students before and after they completed a formal logic course. The results are given below. Do the data suggest that the mean score after the course differs from the mean score before the course? Perform a test at the 5% significance level. I've got my scores on test before and after the course. Since this is a matched pairs design, I need to determine a before minus after. So I've subtracted before minus after and created this third list. This is the list we're going to be working with. So step 1, our hypothesis. Our parameter is u sub d, which is the population mean test score difference before and after completing the logic course. Our null is mu sub d equals 0. Our alternative is mu sub d does not equal 0. Step 2, check assumptions and conditions. We have a simple random sample. It is stated. Sigma is unknown, so we're going to use a t-distribution, and the populations are dependent. Taking our third list, creating a normal probability plot, and based on the linearity of the normal probability plot, we have an approximately normal distribution. Step 3, to calculate the test. So, we needed to find a sample mean and sample standard deviation from this third list. The sample mean was 3.7 and the sample standard deviation was 4.945. Plugging these in, we have 3.7 minus 0 over 4.945 divided by the square root of 10, and we get t equals 2.366. Since this is a two-tailed test, we're going to draw a line at 2.366 and shade to the right, and at negative 2.366 and shade to the left. The right side p-value is 0.021. So the probability that we get a sample mean difference equaling 3.7, given that the population mean difference is equal to 0, is 0.042, which is the double of the right side. Our conclusion: since p-value is less than alpha, we reject that there is no difference in population mean test score difference before and after completing the logic course.